Hello. In this module, we are going to develop ch3-PG model. Ig meaning ideal gas and PG meaning perfect gas. So let's begin with the assumptions underlying these models, and it will become clear what we mean by Ig versus PG model. So the assumption number one, which is valid for both ideal gas and perfect gas, is that is called the equation of state. Ideal gas, which is the familiar PV equals nRT from your chemistry. So this is the first form of this equation. We'll develop 4 different forms, but make sure we understand what unit to use. Pressure must be absolute pressure in kilopascal. This is volume in meter cube. N is in kilomole. Recall the definition of N, mass over molar mass. And R bar is called universal gas constant. Its value is 8.314 kilojoule per kilomole Kelvin. It never changes. And temperature must be in Kelvin. So this is our first form. But for engineers, there are some easier forms. The chemist loves this form. And to get the other forms, we just substitute what N is, M divided by M bar, R bar T, or we can simplify this as M R bar over M bar T. R bar over M bar, notice, is called the gas constant. It's not universal anymore because R is R bar over M bar, depends on the molar mass of the gas, on the identity of the gas. So therefore, the form becomes PV equals, is the same equation expressed differently. This is our form number 2. So these become very handy. Suppose you want to find the mass of a gas, then you can use directly. If you want to know the mole of a gas, then probably form number 1 is better. So what is the unit of R? Because R bar, if you manipulate the units of R bar and M bar, you will see the unit will become kilojoule per kgK instead of per kilomole Kelvin. Okay, what are the other forms? There are 2 other forms. So if we start from PV equals mRT and just switch sides of the mass, so P V over M equals RT, which means P specific volume RT. So this is our form number 3. It's very valuable to find when we want to find the specific volume from pressure and temperature. And finally, the last form is used mostly in fluid mechanics. This implies P equal 1 over VRT, which means P equals rho RT. So if you want to find density of a gas, the 4th equation is the best. Just to show you how do we find the value of molar mass, etc. To do that, there is in the tables, if you go to the perfect gas model and the common gases, that table will have the values of molar masses for different gases. As a matter of fact, even R is tabulated for different gases. We'll come back to Cp, Cv, and K in a moment. So if you go back, so we now know the assumption number 1, which is valid for both PG and Ig model. So let's list the assumption number 2 for the ideal gas and perfect gas model. It is that U is a function of temperature alone. Mathematically speaking, U is UT. Actually, it is a consequence of the first assumption, but it needs a lot of theory to prove that. So we just use that as an assumption here. Let's keep that in mind. And the final assumption, so this assumption is valid for both, again, for both Ig and PG model. But assumption number 3 says that Cv is a constant, and that defines only the PG model. So the PG model is really a subset of the IG model. So in other words, the PG model, which is the simplest of all gas models, and which is the model we are going to use the most, assumes CV to be constant. As we saw, you can go to the table and take a look and find the value of CV for different gases. And just to make sure, let's introduce one more term. The ratio of CP and CV is called K, specific heat ratio. It's called specific heat ratio. We'll use that later on, but it's good to introduce that property right away. Okay, so it's clear what our assumptions are. Assumption number one is ideal gas equation, commonly known ideal gas equation, PV equals RT. Assumption number two tells us U is a function of temperature alone. Very important. So it tells us that for a gas, internal energy doesn't depend on pressure at all. Amazing. It's true. Assumption number three is a simplification for the perfect gas model. CV is constant. So armed with this assumption, let's see how we can find VUHS, the thermodynamic properties, or we are mostly interested in their difference, how we find. So let's start with finding V. Of course, we'll use PV equals RT. So this problem has been solved. So if you know a state 1, you can find V1. You can know state 2, find V2, find the difference. So that's very simple. Okay, now let's go how to find U. Okay, you recall the thermodynamic relation that we developed earlier. It tells us this is true for any pure substance, not just a gas or a liquid or a solid. So starting with this relationship that we developed from state postulates, if you recall, we recognize that U being a function of temperature alone, this partial becomes zero because U is a function of temperature and we are holding temperature constant. Therefore, U must be a constant. Therefore, this whole term goes away. And that simplifies things quite a bit. So this is true for both. See, we haven't used the assumption number 3 at all yet. So therefore, we can see that since U is a function of temperature, therefore CV must be a function of temperature also. See if that makes sense to you. Of course, for a perfect gas, CV is a constant. So let's, for the sake of simplicity, just stick to perfect gas model development. Okay, in that case, how do you find delta U? We integrate this equation from state 1 to 2. So for delta U, which is U2 minus U1, is integral CV dt. Of course, for the IG model, we have to evaluate the if we evaluate this integration, CV as a function of temperature has to be integrated. That's why there is tables of gas properties are written for ideal gas model. But if we use the PG model, we recognize that CV is a constant. CV will come outside. It will become very simple. So we get a simple formula for finding change in internal energy for a perfect gas, which looks very similar to SL model. If you go to the SL model, you'll find the formula is identical. Okay, now let's try to find enthalpy, specific enthalpy, H. We know from the definition of enthalpy, it's U plus PV, and that means we can PV equals RT, we can use H equals U plus RT. If I take the differential of both sides, it becomes dH equals du plus R dt. R is a constant. And we have already shown that du is CV dt in the previous slide, R dt. So this equation reduces to the differential of enthalpy become this. And this is from the basic definition. This is true for both ideal gas and perfect gas, by the way. Also, if I start with the thermodynamic relations, we could write dH to be Cp dt, if you recall, plus del H del P at constant temperature dP. Now notice that from this equation we recognize, suppose we call this equation number 1, we recognize that Cv we already proved is a function of temperature for ideal gas, and it's a constant for perfect gas. R is a constant, and this is also temperature, so H must be function of temperature alone. If we recognize that, and in this partial we are holding temperature constant, therefore any derivative of H will be 0 because enthalpy is now a constant. So this term goes away. So the equation number 2 tells us that dH is Cp dt, and equation number 1 tells us dH is Cv plus R times dt. So therefore, this must be equal Cp. So we come up with this important relationship that Cp must be equal Cv plus R for both Ig and PG model. Notice that in Ig model, Cv will vary with temperature, therefore Cp must also vary with temperature. However, in a perfect gas model, they're both constant and they're all tabulated. They become the material properties. So, in terms of formula for enthalpy change, delta H, which is H2 minus H1, is integral Cp dt now, going from 1 to 2. This will be the ideal gas model, and perfect gas model will be simplified because Cp is a constant, so it will come out of the integration, and we come up with a very simple equation for finding enthalpy change. So we have one equation for change in internal energy. Now we have an equation for change in enthalpy. Finally, we need to develop an equation for change in entropy. And if we start from the TdS, the first TdS relation, then we can go, notice du is Cv dt divided by T plus PdV over T. Note that using PV equals RT, the ideal gas equation, we can substitute P over T as R over V. So the equation reduces to Cv dt over T plus R dV over V. If we integrate this from state 1 to 2, and recognizing that for the PG model, Cv is a constant, the entropy equation becomes delta S, or S2 minus S1, is Cv ln T2 over T1 plus R ln V2 over V1. Similarly, if we started from the other TdS relation, remember there are two TdS relations, TdS equal dH minus VdP, then we'll end up with delta S equal S2 minus S1. It's in the book. I'm not repeating it. It's very simple to derive exactly the same way. The purpose of these two different equations that in case we know pressure ratio and temperature ratio, we can find change in entropy, whereas if we know the volume ratio and temperature ratio, we can find entropy change from that equation. But what's amazing about these entropy equations is that if entropy is constant, and we'll find many practical situations where we'll find a system has undergone a change, but the entropy did not change. In that case, notice that we get a relationship between temperature ratio and pressure ratio here. For instance, if delta S is 0, you can write now, these kind of relationships are known as isentropic relation. And for a gas, these relationships plays a very important role. And it can be even further simplified. Instead of having CPR different constants, if you recall what K is defined as a ratio of Cp over Cv. We also know that Cp was shown to be equal Cv plus R. We did that, I think, when we proved that in this equation that dH is given by equation number 1 and 2, one of the consequences, I forgot whether I wrote that down or not, is that Cp must be equal Cv plus R. So that is a powerful conclusion that I forgot to mention about. Because if you look at equation 1 and 2, that's an obvious conclusion. So this is always true for ideal gas or perfect gas. Yes, we did do that here. I'm sorry. So going back, if I use these two relationships together, we can express Cp and Cv in terms of K. Just by manipulating these two equations, you can show that Cp would be given by Kr divided by K minus 1, and Cv is given by R divided by K minus 1. So then, here we need a Cp over R. So you can see that Cp over R can be replaced by K divided by K minus 1. So therefore, this relationship becomes even simpler. K divided by, okay, let me write that in a new page. K divided by K minus 1 ln T2 over T1 equals R ln P2 over P1. No, sorry, R is already gone. R we have absorbed, which means, if you recall the definition of log, so what we obtain is that if entropy remains constant, we can relate temperature ratio and pressure ratio by this simple equation. If we tried with this other form, the other entropy expression, we'll get similar result for volume ratios. And these are all summarized in, if you go to table J, equation, the formula sheet. I would urge you to print that out, because when you solve problem manually, this could be very handy. So once again, you can see that general equations which are valid for all models, and then we have summary of SL model, and then here is the PG model. Notice that, you know, this PV equals RT, the different form is expressed in this first equation, equation number 8. Then delta U, delta H, these relationships are here. Delta S, we just showed these two different relationship of delta S, how to find. And finally, if entropy remains constant, notice a whole slew of equations can be obtained based on what you know. Suppose we know the volume ratio, you can find pressure ratio. Suppose we know the temperature ratio, we can find volume ratio. So in other words, these equations based on, these are, all of them are kind of connecting different variables. So pressure ratio is here connected to temperature ratio, density ratio. So any of these equations can be used. Okay, sorry, there are basically 3 different equations here. They can be used for connecting two states where entropy remains constant. As we solve some examples with these models, it will become very handy. These equations will be your big friend in solving an isentropic problem. So once again, we have covered the SL model, the PC model, and the PG model thoroughly. And the IG model, even though we have covered the outline, we are not going to use much because it's more it doesn't give you as much insight, where the PG model is so simple, will give you formulas that we can understand a problem, we can appreciate the parametric dependence of a problem on different properties. And you'll find the PC model summary is also here. And the one model that we are skipping is RG model. Even though it's called real gas model, actually this is the most inaccurate of all models. Essentially, in a real gas model is a universal model for any gas. For instance, it can be used even for PC model. So not a PC fluid, a phase change fluid. So the RG model is a universal model that tries to fit any material in one unified model. It's theoretically very appealing, but its practical importance is only limited to fluids for which there is no table available, or a fluid which cannot be modeled by the perfect gas model or ideal gas model. So we'll stop here and we'll solve some examples of finding properties of gases which can be modeled by perfect gas model.